Hello, everyone. My name is Jing Wang, and I'm a postdoc from the Department of Materials at Imperial College London. And my presentation today is understanding the mechanical performance of lanthanum iron manganese silicon-based magnetochloric material via multi-scale mechanical testing and atom probe tomography. So this work is a collaborative work between Imperial College London, where we carried out the mechanical testing of this material across length scales, and Max Planck Institute at Düsseldorf, where they carried out the atom probe tomography analysis. And Cambridge Technology is a company based in the UK who supplied all the raw materials used in this work. To just give you a brief background of this work, so we studied lanthanum iron manganese silicon-based magnetochloric materials, which are intermetallic materials. So the so-called magnetochloric effect is a phenomenon that results in the temperature change of material in response to a changing magnetic field. And therefore, materials with this kind of properties can be used to generate cooling power. And specifically, the cooling efficiency of this material can be higher than the conventional gas compressors, and therefore it has the potential to reduce carbon dioxide emission from the cooling industry. And interstitial hydrogen doping or hydrogenation is used to tune the Curie temperature or TC of this material. And this is for it to be functioning at different temperature ranges, and therefore this material can be used in a wide range of different cooling applications. But a in-service problem for this material is that it undergoes a volume change upon magnetic phase transition, which can subject the material to 3D volumetric stress, and this in some extreme cases can lead to the cracking issue due to, one, the material being intermetallic itself, so it can be quite brittle, and two, it was found that hydrogenation can further decrease the strength and ductility of this material. And specifically in this work, we want to understand why and how hydrogenation decreases the overall mechanical properties of this material. So firstly, we carried out electron backscatter diffraction analysis of this material to study what phases are there in this material and what the grain size is for each individual phase. And we found that, so in figure B here, which is the phase map generated using our EBSD result, that the vast majority of this material, of course, is the lanthanum iron manganese silicon-based intermetallic phase, which is the so-called 1 to 13 phase. And additionally, there is this alpha iron phase, which was introduced intentionally into this material to improve the overall ductility of the material and to stop the cracks in the 1 to 13 phase from propagating through the material. The average grain size in the 1 to 13 phase is about 10 micron, and there's no texture present in the 1 to 13 phase of this material. And then we carried out 3-point bending tests on plate specimens of both hydrogenated and as received, which are the non-hydrogenated specimens. And what we found here is that the hydrogenated plates showed much lower fracture strength and fracture strain than the as received plates, indicating that hydrogenation has decreased both the strength and the ductility of the materials, and we want to understand why this has happened. And therefore, we examined the fracture surface of these two sets of specimens to see if we can see any difference in there. And interestingly, the fracture surface of the as received specimens indicates that the crack path is intergranular because we can see the 3D nature of the grains clearly on the fracture surface. But for the hydrogenated specimens, the fracture surface is nearly completely flat, indicating that the crack path is transgranular. This suggests that the hydrogenation has posed a weakening effect specifically on the grain interior or the crystal lattice of the material. And so we want to understand the details of this weakening effect. And that requires testing of single crystal specimens. And because we already know the crystal orientations of the grains from EBSD, and then with focused ion beam, we were able to fabricate single crystal specimens within grains with specific crystal orientations. And here we chose to test specimens with three groups of different crystal orientations, where they have their 001, 011, and 111 directions pointing upwards, and therefore we test along all the low index directions of this FCC structure. And as we can see on the SEM images of the micropillars post-deformation, despite all the different crystal orientations and whether the sample has been hydrogenated, all the micropillars exhibit highly similar mechanical behavior, where the applied deformation is accommodated by localized shearing. But if we compare the failure strength of the pillars, between the two sets of samples within each group of crystal orientations, we can see that some of the pillars in the hydrogenated sample are weaker than the pillars in as received sample with the same crystal orientations. For example, the red and yellow curves, which corresponds to the 001 and 011 oriented pillars, both show this behavior. But for the purple curves, which are for the 111 oriented pillars, the difference in failure strength is negligible between these two sets of materials. So clearly this weakening effect by hydrogen atoms is anisotropic in this material. And once again, because we know the crystal orientations of the pillars, we were able to extract out the Miller indices of the shear planes observed on these pillars post-deformation. And it turned out that for the 001 and 011 oriented pillars, where we observed clear difference in strength between the as received and hydrogenated specimens, the shear planes are 111 planes. Well, for the 111 oriented pillars, where there is negligible difference in strength between the two sets of specimens, the shear planes are 001 planes. And then we want to take a step further to understand whether this is due to a difference in the arrangement of hydrogen atoms on these two sets of planes. And we studied this using atom probe tomography. And so we lifted out atom probe needles from the main phase in both the as received hydrogenated specimens, and we observed that the hydrogen content in the hydrogenated specimen is much higher than that in the as received specimen, which is good. And similar to the site-specific fabrication of micropillars based on the EBSD results, we lifted out atom probe needles with 111 and 001 planes parallel to the sample surface, thereby making use of the high spatial resolution of atom probe in the Z direction. And this is for us to study the hydrogen atom arrangement on these two sets of crystallographic planes. And here I'm showing the spatial distribution maps of iron atoms and hydrogen atoms in the non-hydrogenated and hydrogenated specimens. And we can see that in the non-hydrogenated specimen, the distribution of hydrogen atoms is completely random in the crystal lattice. And this is reasonable because the hydrogen atom signal for that specimen should not be from the material itself, but more likely from the atom probe analysis chamber. And when we look at the hydrogenated specimen, we can see clear evidence of ordered hydrogen atom arrangement on 222 planes, but nearly random arrangement of hydrogen atoms on the 002 planes. And this is interestingly consistent with the anisotropic effect of hydrogen atoms on the mechanical properties that we observed previously, where we see that the weakening effect is most significant when the shear plane is parallel to the 111 or 222 planes. And we now know that from atom probe analysis that these are the planes where the hydrogen atoms are arranged in an ordered way. So just to summarize, we studied the mechanical properties of lanthanum ion manganese silicon-based magnetochloric intermetallics, and we found that interstitial hydrogen atoms deteriorates the mechanical properties of this material, and we found that the crack path changes from intergranular to transgranular after hydrogenation, and this indicates a weakening of the crystal lattice by the interstitial hydrogen atoms. And through micropillar compression of single crystal specimens with controlled crystal orientations, we were able to observe that this weakening effect of hydrogen atoms is anisotropic, where it's most significant when the shear plane is 111, but nearly non-existent when the shear plane is 001. And through atom probe tomography analysis, we were able to reveal the ordered arrangement of hydrogen atoms on the 101 planes, which is likely the origin for the change in mechanical properties that we observed in the micropillar compression tests. And for now, we are employing our new atom probe facility at Imperial College to extend this study into the elemental distribution at phase and grain boundaries in this material. And we've already got some interesting results, which hopefully will be shared with you in due course once we put them together. Thank you.